All right, here we are at day 7 of our environmental data science class, and today we're finally going to learn a little bit about using spatial data in R. There's a phenomenal resource for this that's a book by Robin Lovelace and Jacob Nawasad, and I don't know how to say this name, Hannes Munchow. And basically, it's free online. You can also buy it as a book, but it does a really thorough job of sort of answering any question you might have about working with geospatial data in R. I encourage you to read it, and at least before class on Tuesday, read this Introduction to Geographic Data in R and read the vector data section. So for this section of the workflow, we're going to make a new repository, and we'll call it Lagos Analysis. Or that's the description. We'll call it Lagos Analysis. And if you're wondering what Lagos is a pretty sweet data set made by Patricia Serrano, Emily Stanley, and a bunch of other really awesome scientists that basically is a bunch of lake data sets joined together, over I think 400 different lake data sets joined together. And it's a really well documented data set that they built, and it includes data like the clarity of a lake, algae blooms, or information on nutrients, chlorophyll A, and other things that can indicate algae blooms. So it's a really sort of useful data set, and the wonderful thing about it is that they have a package that makes it really easy to download and work with the data directly in R. So that's what Lagos is. So we're going to analyze some of that data for class. We'll keep this repository public. Actually, I'm going to make it private just for this. Oh, I thought it, whatever. Okay, create a repository. And I'm going to clone it as a SSH, because that's what I use. You'll clone it again as an HTTPS. Don't fork it yet, because I'm going to add data in here. So while you're watching the video, just sort of watch along, and then in class we'll fork it and do a separate analysis in class. And I'll open a new RStudio. We'll go back to new project. This should feel familiar now. Version control, git. Here's the URL. It's already in my environmental data science. I just want to make sure it's parallel. Yep, we're going to open that. That's what we want. Lagos class analysis is fine. Okay, now that we have this here, we're going to go ahead and do File, New File, our Markdown now. I prefer that you work on our Markdown from now on in class, now that we've gone over it. I'll call this Lagos Spatial Analysis. And I usually just start when I make a new R Markdown document. I often just delete everything except for the setup chunk. And you'll notice there's this option here that they put in this setup chunk that says include equals false. And what that means is basically it's not going to include any outputs, even though it's going to run the code in here. And that's kind of nice, because it's another way to suppress the messages for all the packages you load. So I kind of like doing that. Here I'm just saving it, so we'll just call this one beginning spatial analysis. And so we're going to load tidyverse. We're going to load a very important package called SF. SF is the sort of main spatial package we're going to use. We're going to load another really sweet package called MapView. That makes it easy to look at data, spatial data interactively. We'll also go ahead and load this package called Lagos NE. And you're probably going to have to install MapView and Lagos NE and SF before we load them. And I'll go ahead and comment what they are. Spatial package. So SF can read shape files, and it can create them. And shapefiles are just spatial data sets. And then this one, interactive maps. Lots and lots of clean. The critical thing about Logos data is that the data set is what's called analysis ready. So it's the data in here is actually pretty clean, unlike if you've worked with the water quality portal or other data sets like that, where you have to do a lot of the cleaning yourself. And then tidy packages. So one of the first commands you might want to have, you're going to have to look up is the Logos commands. So we'll load these packages. And a nice thing that they do when you load Logos is they tell you where to get more information and how to cite the data. So if you use this in a paper, you just always want to make sure you cite this. So I'll rewrite this question mark because I'm trying to get at the Logos get. So the Logos get is a way to get Logos data onto your computer. And so here they just sort of run the default. So we want to get the default to the latest version. We're going to go ahead and say Logos Northeast. They've only published the data for the Northeastern United States. That's why it's called Logos NE. And we're just going to say that it goes into the common path that it normally goes into. So we'll go ahead and run this. And it's going to just download essentially all of the Logos data from the internet directly. And then it's going to store it in a file on your computer. And it's always going to know where it is because it's associated with the data set. So in this case, normally I talk about putting a data folder in here. But in this case, we're going to be only working with data to start, at least, that's already in our Logos sort of data set. So we don't have to move that data around. So this download might take a while. So once that file is finally downloaded, you should get a return that looks like this, and it tells you all the different pieces of information it's downloaded. And after you've downloaded that data, you need to load it into R. So we're gonna have to do another command. I'm just gonna comment that this is the download script. And if you run this again after you've downloaded it, it'll say that you've already got it, and you have to force it to overwrite it. So in this case, it doesn't matter if we sort of leave that. It's nice to know that we already downloaded it and that it's fresh. And then I already just asked, how do I load this data? And because I kind of forgot. So we'll go to Logos, I need load, and basically you just can say load. It looks like you can say that the version is null, and it'll just pick up the newest one. So let's see if we can do that. We'll just call it Logos, and we'll do Logos NE load. And what it's going to do is just open up the newest version. And it looks like it's good that we left that version open, because if we had filled it in, like in the help file in the bottom right, we would have gotten an old version. And that's not something we wanted. When you load in Logos data, you get a list of 37 different objects. So when you have a list like that, lists can hold data frames, vectors, spatial objects. It can hold all kinds of stuff. So the first thing we might want to do is just sort of check out what's in that list. Okay, it looks like there's some county information, there's land use, land cover change. There's all kinds of different stuff in here. I know from experience the thing that we want to look at where these lakes are is this thing called the locus. And the locus is the lat long of the center of a bunch of lakes in the US. So we'll just say lake centers. And here we'll do Logos locus. And the little $sign here is just calling that named list. So now we're just getting this thing called locus. And now we have a very large data frame with 141,000 observations of 18 variables. So from there we have most of the data we want to play with loaded in. So maybe let's make a new chunk, and we can write some stuff up here that I'm going to actually split out this so that we can see it. And what I just did there to split that out, I went up into the code itself. I hit enter, and then I hit Control-Alt-I, and R does this clever thing where it knows to cut off this chunk so I can make a new one. So I inserted a chunk inside of a chunk, and it knew that means that I want to close off the next one. So I'm going to not call this the setup chunk. I'll call it the data read. And I'll say the title of this whole thing is probably, or the first level of analysis is that this is the Lagos analysis, is all we'll say. And then we'll say loading in data, first download, and then specifically grab the locus or site lat logs. So this gives us sort of location. And we've already run that, and grab the lake centroid info. Okay, so now that's commented well and a little bit more understandable. And now we have this thing called lake centers. So maybe something I always like to do when I have a new data set is I like to look at the names. So I'll go names, lake centers. Okay, it looks like it's got a bunch of different columns. It has Lagos Lake ID, so that's going to give us an ID for this data set. It has an NHD ID. NHD is just a national hydrography data set, so it has IDs for all the lakes and rivers in the country. Then it has a bunch of other information that we might use or might not use. It sort of tells us where it is geographically, what HUC it is, so that's basically what watershed is it in. The piece that we're going to first play with is this NHD lat and NHD long. So this is just saying what's the lat and long of this data. So here I'm going to say convert to spatial data. So that just gives us the name, but maybe we should look at the structure before we go ahead and start manipulating the data. So let's look at structure, lake centers. Okay, so we have this NHD lat and NHD long. It's a numeric and it's a decimal degree lat and long. So that's helpful. That's good to know. And I'm going to actually say look at the structure. And I'm going to comment that out because I don't want to look at the structure every time, but you can at least know how to look at the structure and then look at the column names. So names, I'm just going to automatically comment it out. And then finally, if you really wanted to see the data, you could view the full data set. And you could do view lake centers. When you view large data sets like this, you want to be careful that you don't load too much because it can bog down R. So like if this was 1 million points, it just can take a while. So one nice way to look at less data is you can either index it sort of in a base R style where you say, hey, I want the first 100 rows, and R goes by rows is the first index and the second one is columns. So I'm asking for the 1 through 100 rows, and if I leave this blank, it means of all columns. So I'll go ahead and do that. And now I just have 100 rows instead of 100,000. In the exact same way, you could do view lake centers and you could do slice 1 through 100. And slice just means it's going to grab the first 100 rows. So we'll do that. That's the sort of tidyverse version. And now we can look and we can actually see what the names of these things are. So there's a bunch of different ponds, Latin long and lake area, etc. And then we want to do something where we take what is essentially a data frame. So again, when we did structure, this says this is a data frame. And we want to convert that to a spatial object. So how might we do that? Well, there's a sweet function in the package called SF that is called ST as SF. So it's saying, I want to take a simple table in ST and I want to turn it into a simple feature, which is a spatial object. And so here is sort of how you do that, and you can do it with a bunch of different things. You can do it with polygons, you can do it with points. Here we have point data. So I happen to remember that the way you do it with point data is you assign the coordinates, the long and lat. So we just need to sort of take our data set and we'll call it spatial lakes, and we'll do ST underscore as SF, and we'll do lake centers, and then we'll do chords. And here we need to figure out if long or lat comes in first. So we'll go ahead and look for chords again in the help file. So chords is in the case of point data. Names are numbers of the numeric columns holding coordinates. Okay, well, it doesn't tell us the order still. So, okay, it looks like in their example, you have X and Y. I always get this confused, but essentially that means that we want to have lat first. So latitudes are the X, So that's going to be this column called nhd_lat. And then we want to have long next. And we're going to go ahead and call this command. And now we have this thing called spatial lakes. And maybe we want to look at a subset of the data. So we'll say subset spatial. And we'll do spatial lakes. And we'll again slice this 1 through 100. Let's just see what the first 100 returns look like. And here's where we'll use another new function called map view, dynamic map view. I can't see what I'm writing because of that thing. Map viewer. And we'll do map view subset underscore spatial. Okay, so now what we can see here is that these are plotting these points, but if you notice, I should be able to add some base maps to this, and there's no context. So we should see something like Minnesota, Wisconsin, or New England, so, or somewhere in here we should see other states. So something went wrong when we read this data in. And if we look at STSSF again, so we go back to our help file, we have the coordinates in there, but we're missing what is called the projection. So we need to know essentially how is this data projected. And the way you do that is with what's called a CRS. So we can look if that's in here. Yeah, so this basically it's in these extra ... means additional options that it's not going to go over here. But it could include named arguments like CRS or precision. And what CRS is, this is not a JS class, so I'm not going to fully explain it very well. But a CRS is basically the projection system that projected out the data. And if you've taken a GIS class, you know that knowing your projection system is really important. Lat longs and decimal degree are often projected in WGS84, which I happen to know the code for is 4326. If you don't know the code, you can go ahead and look it up. You can say WGS84, and then the code that we're entering is called an EPSG code, and it's just a way to simplify projection information. But you can go to these spatial reference. Normally you can go to those. Well, that one's broken. Oh, there it is. So you can go to these spatial projection ones, and it'll tell you, okay, the code is 4326, and it's, again, in lat long in degrees, so it looks like the data we have, which is nice. And then you can see where does it cover the globe, I think. Maybe you can't. Normally there's a map over here, but this site looks weird today. So anyways, that's how you can sort of figure out your projection. Frequently this is going to be like, you know that your data is in NAD 83, and so you could look up like NAD 83 Colorado EPSG, and you'll get these different projections. So that EPSG would be 2232. So there's all these different projections. Again, this is not a GIS class. This is a bit of here be dragons. You really, really need to know your coordinate system before you play around. If you're working directly with shapefiles include the coordinate system. But here, we'll add this coordinate information so that the simple features function knows that this is in the WGS84, which is a global projection. So we'll rerun that. We'll take the subset again. And now let's try the map view again. Okay, turns out the first 100 examples are somehow in Antarctica. Or, that's not very likely, right? Look at the world imagery. Okay, no, there's definitely not the right one. So, as I frequently do, I got the long and lat backwards, I would assume. So I just rerun this. Again, I resubset it. And now we have some sensible data. So now we can look. We're in Minnesota. We can see if indeed these points are about at the center of these lakes. And that's exactly what they are. You can quickly change the background imagery so you can see, like, is this an algae bloom looking lake? Is this a clear lake? And we just have the first 100. But this is a large data set of 100,000. I wouldn't recommend using this map view function for more than 50,000 points. It can get really slow. But this is sort of the just first step. And so you usually want a subset when you're plotting out big data sets. So I'm just going to say subset for plotting. But indeed, now we have it right. Spatial lakes looks like it's working. And then our subset just helps us map the first 100 points. All right, it's a new day, but we're still in here coding on this Lagos data set. And we just plotted this subset of spatial data. And we just subsetted that kind of randomly with this slice function. But what if we wanted to subset it by, maybe we only want data from Iowa or Minnesota? I'm going to show you how to do that, but first we need to load in data from that includes shapefiles of the United States. So we're going to load this package called USA Boundaries. And what that has is what it sounds like. It's USA states and counties. And you'll probably have to install this to get this to work. But what USA Boundaries allows us to do, we'll add another section here. Subset to only Minnesota. So what US Boundaries allows us to do is it allows us to just immediately load from the internet a data set of USA polygons for states, for example. So we'll do states, and we'll do US states. We'll just call this function. And when we do that, it returns this object called states. And let's go ahead and look at the structure of states. So states is an SF object, so it's already a spatial object, and it's a data frame. So it means it has two types of objects. And the data frame part, it's filled with these things called the state FIPS. So this is a FIPS code, which is just a code for identifying states. And it has some other geocodes. What we might want to be able to filter on is something like name. So we have this object called states, but we want to make it just Minnesota. So I'm just going to call it Minnesota, and I'll go states. And just like a regular data frame or tibble, we can actually filter this data, this spatial data, directly in R. So we can say filter name equals Minnesota. I probably spelled it wrong, but maybe I'll get it right. And now we have just one object called Minnesota. And if we want to check what's in these files, we can always do a map view. So states only has 52 observations. So let's go ahead and do states map view, or map view of states. And there we go, we got it. We have Hawaii over here, got Puerto Rico. So we have all these states. If you click on them, some of the information pops up. Okay, that's great. And then we can also go ahead and I'm going to comment that out. I'm just going to say if they loaded. And then I'm going to comment that out. And then now let's check if Minnesota, indeed, when we filtered on Minnesota, we got Minnesota back. Great. So now we have an object of Minnesota. We also have this object of spatial lakes. And so what we can do is filter the spatial lakes to only be Minnesota lakes. And the way we would do that, there's two different ways. One is a really simple way where you subset with this function where we are going to subset with a square bracket. So we do Minnesota, or sorry, not Minnesota. This is going to be lakes, spatial lakes. We're going to subset spatial lakes. And I lost my tick marks. There we go. Spatial lakes. With square brackets. And we're going to say we only want the spatial lakes inside of Minnesota. So we'll do Minnesota. And we'll do a comma. And that says, hey, I only want the rows of this spatial lakes data set that are physically inside of this polygon. So we'll do that. And here it throws out a warning. Although coordinates are longitude, latitude, ST intersects assumes that they're planar. And this is an important warning where you should really understand your data set before you assume that this actually worked. And that's because if we look at the projection system of Minnesota, it's still in this EPSG 4326, which is a global projection. And so it's actually not projected directly onto a flat surface. It's actually projected onto a global surface. So it's when it says it's planar, it's saying, we assume that you've already done this work to make it a planar thing. So to fix that and to make sure that our data sort of actually matches up, we can do another command where we transform the projection. So now we're going to project it onto what's called an equal area USA projection. And that, I just happen to know the EPSG for that is 2163. And so now Minnesota will be in this new projection called 2163, and then we can try to subset it. But here we're going to get an error because they're in two different projections, and you can't subset when they're being projected in two different projections. So here it says STCRS does not, the two STCRSs doesn't work. So to fix that, we can go back up to Spatial Lakes. Here we told it the original projection is 4326, but maybe you want to transform it to this equal area projection. And so we'll do 2163. And now that'll be an exact same projection. This command will take a little bit longer because it has to project out 141,000 different points, but it's actually still pretty fast. And now we still have Minnesota in the same projection. And then now we'll do this subsetting. And if you see, we've lost this error. So we've lost that error. And then this Minnesota Lakes is actually still 29,000 observations. That's right at the limit of what map view can handle. So I'm just going to say subset lakes based on spatial position. And then here, we'll go ahead and still subset the lakes, the Minnesota lakes, just to not plot a million of them, but we'll just keep 1,000 this time. And I'm just going to pipe that through. And I'll just do, so here I just called this Minnesota Lakes object. I'm saying keep the first 1,000 rows and then pipe that forward to a map view. And there we go. We've got 1,000 lakes plotted. They're all over Minnesota. They have all this information if you click on them, so we can plot them by lake area. Another thing that we might want to do when we're plotting this many lakes is maybe we want something about the lake information in here to color the different bubbles. So maybe let's color it by lake area, which is called lake area in hectares. So we'll do, there's this function inside of map view where you can say, or not function, an option where you call it zcall equals lake area hectares. And so now it's going to go through and color all these lakes by different colors. So basically the vast majority of them are less than 5,000 hectares, and then there's some big ones in the midst of that. If we wanted to make that plot a little bit nicer, we could also arrange the data by lake area. And we would want that to be descending, so we'll have the, or no, actually we want it to be ascending. We'll have it so that the smaller lakes are plotted first and the big lakes plot on top of them, and hopefully that'll make some of the bigger lakes pop out from the background of lots of the small lakes. So there's not that many big lakes, but you can see that this dot here is plotting over the ones adjacent to it, and same with the yellow dot. They're plotting last, so they show up sort of on the map better. Okay, so now we're just going to say plotting the first 1,000. Okay, I think this video is at about 30 minutes, so we'll stop here. And in class, what we'll try to do is we'll link some of this lake spatial data directly to lake water quality data, and we'll sort of see if there's any spatial patterns of lake water quality in Minnesota.